So in this video, we're going to review atomic structure, and then we're going to talk about isotopes, and then we're going to learn how to calculate half-life. So just a quick review of atomic structure. We all know that atoms have protons and neutrons in the nucleus of an atom, and we see that protons and neutrons both have a mass of 1. Electrons are in orbits around the nucleus of an atom. So you can see here we have a Bohr-Rutherford diagram for aluminum. So we have the protons and neutrons listed in the middle, followed by our electrons on rings. And we basically say that an electron has a mass of 0 because it's so small. I mean, you can see that number there. It's so teeny tiny that they really don't really give much to the mass of our atom. And when we write elements in standard form, we always have the element symbol, and then we have the mass number up top and the atomic number from the periodic table at the bottom. The atomic number here tells us the number of protons, and if we do the mass number minus the atomic number, we get the number of neutrons. So I always like to say that the big number is going to go on top, small numbers down at the bottom, and then we're just going to do big number minus small number to figure out our number of neutrons. So let's just review a Bohr-Rutherford diagram quickly. So this is for carbon-14, and so you can see this is in standard form. So we have the big number, we have the small number. So what I like to do is just kind of do like old school subtraction. So 14 minus 6, so we get 8 neutrons. So we have 6 protons, and we have 8 neutrons in our nucleus. And then we can put 2 electrons on the first orbit, and then we can put up to 8 on the next. And we are always going to start with our electrons single and then pair them up. So that is our 6 electrons. So that's actually that's it. That's our Bohr-Rutherford diagram for carbon-14. Now you may be asking yourself why carbon-14, because usually we talk about carbon having a mass of 12. Carbon-14 is a specific isotope of carbon, and an isotope is something that has the same atomic number because you can't change the number of protons, but it has a different number of neutrons, so it has a different mass. And so here are 2 fairly common examples of isotopes. So we have carbon-14. Carbon-14 is inside all of us right now, and it's helpful for figuring out how old something is. So if you were into dinosaurs when you were a kid or anything old like that, they use carbon-14 dating to figure out how long something's been dead. And then we also have 3 different isotopes for hydrogen. So if you look at the mass of hydrogen on the periodic table, 1 is the most common form, but deuterium is considered, if we use water that's made with deuterium, that's considered heavy water, and that's really important in nuclear reactors. So if you have a known mass and you know the half-life of a substance, you can actually figure out how long something has been gone for. So we use decay and half-life carbon-14 dating, but we can also use it for a bunch of different things. So here's our formula. So you are going to have to either use your bracket function or your fraction button on your calculator when you're doing that exponent, because you are going to have to do the time divided by the half-life. And AO is your original mass or your initial mass, and that's the mass that you have, and we're usually calculating the mass. Half-life graphs are exponential curves, and they're exponential decay curves. So if you're taking the grade 11 university math, you've probably looked at, or you will be looking at, exponential curves. And so half-life graphs, you will probably see them in your math class because it's a real-life application of exponential curves. So again, this is a graph of the decay of carbon-14, so you can actually figure out how old something is based on the mass of the carbon-14 that's left. So let's look at an example. So here we're using neon-19. The fact that it's neon-19 really doesn't matter. So we have a half-life of 17.2 seconds, 22 seconds. And it says, what mass will remain after a 250 gram sample after 1 minute? So we do need to make sure that our time values are in the same units. So we're going to make that 1 minute 60 seconds. Now, the other thing too, you can leave the mass in grams, but if you're afraid you're going to forget, feel free to change it to kilograms. So here's our formula. So let's go ahead and put our information in. So again, you're going to have to use the fraction button on your calculator or the bracket function. So what I would do on my calculator is I would do 0.5, and then I'd use my x to the power of y button, and then I'd open my brackets, and I would actually type in 60 divided by 17.22, close my brackets, hit equals, and then I would multiply it by 250, and you get 22.3 grams. So let's leave it at that because the 1 minute is kind of skewing our sig figs. So let's leave it at 22.3 grams. And that's it. That's all there is to calculating half-life. Now, if you're asked to figure out how much time is remaining, you can either model that with a curve, or you can use log or your natural log function that maybe you've learned about in math class, or you can just do it with trial and error.